We're going to do a little review of basic atomic structure, ways in which we represent it, things like atomic number, mass number, what these terms mean. We're also going to take a look at how we represent processes such as radioactive decay. We're going to talk about alpha emission, we're going to talk about beta emission, we're going to talk about something called gamma radiation. And again, we're going to talk about the ways in which we represent these processes. There are three main subatomic particles that we worry about in chemistry. There's the proton, the neutron, and the electron. The protons and the neutrons, if you remember, exist within the nucleus, and they are surrounded by the electron cloud. The space surrounding the nucleus is where you will find the electrons. Each of these are particles. They have mass. They have a very, very small mass. And I have in this table representing or showing you the masses of each of these. Protons and neutrons have a mass that is very, very close in size to each other, so close that for the most part we're just going to say that they both have a mass of 1 atomic mass unit. Electrons are so very small in comparison that a lot of times you'll hear that they have a mass of 0, although in reality they do have a mass approximately 1/2000th of that of a proton or neutron. The other thing that's important about these subatomic particles is that there is a charge associated with them. For protons and electrons, they have the same exact charge, only the magnitude is opposite, so protons are positive and electrons are negative. The magnitude of this charge is expressed in the SI unit called a coulomb, and again that charge is very, very small, on the order of times 10 to the negative 19th. And our neutrons are neutral. Now, while this is a charge with a certain value in the units of coulombs, a lot of times in chemistry we're just going to refer to the relative charge. So we do not care exactly what the charge is in coulombs. We'll just say that the protons and the neutrons have the same magnitude charge but opposite. Therefore we say a proton is a +1 charge, the electron is -1, and our neutron has a relative charge of 0. When we put these subatomic particles together, we end up with atoms. And depending upon the number of these subatomic particles, that's going to determine the type of atom. The most important particle with regards to determining the identity of an atom is the number of protons. And whatever the number of protons are, that is referred to as the atomic number. So this is the number of protons. And again, that's what determines what the element is. If you have 1 proton in the nucleus, then that's going to be hydrogen. It doesn't matter what the other subatomic particles are or how many you have. The mass number is the number of protons in the nucleus plus the number of neutrons. So those two things added together give you the mass number. And something we're going to talk about here in a short time is the atomic mass, and this by definition is the average mass of an atom of a particular element. The reason why we have an average mass is because we have more than one type of each of the elements, or more than one type of atoms for each of the elements. So we have to have what's called a weighted average, and we'll do that calculation here in a second. So how do we represent this? If we go back up here, we take a look. If you're talking about carbon, the most common form can be represented as C-12, that is carbon 12, and that 12 is what we have already identified as the mass number. So that's the number of protons and neutrons added together. Now, since it is carbon, carbon is identified as the element with 6 protons. So that must mean that carbon 12 also has 6 neutrons in it. We can either represent it this way, or we can represent it with this format where we have a symbol carbon. The superscript number is our mass number, and our subscript number is our atomic number. Now, there is carbon 12, there is also carbon 13, There's carbon-14. Carbon-14 is the one that people are familiar with in hearing because that is the radioactive form, and that's what they use for something called radioactive carbon dating. Carbon-12 is the most common form. But the thing is that we have carbon-12, 13, and 14, all of those forms in any sample of carbon, and that includes us. We are a sample of carbon. We have carbon within our bodies, and so we have a certain percentage of carbon-12, 13, and 14 in there. Now, the amount of carbon-12, 13, and 14, that percentage is pretty constant, and so that's why we're able to figure out what the average mass is based upon that. Now, before we do that, I just want to briefly remind everyone that carbon-12 is our basis for our atomic mass unit, or our mass, the mass unit that we use in chemistry when we talk about the mass of protons, neutrons, and electrons. So the atomic mass unit, by definition, is equal to 1/12 the mass of a carbon-12 atom. It is defined that way, so that means it is exactly 1/12. So by definition, that means that if you have a carbon-12 atom, its mass must be exactly 12.000, and I could continue writing zeros here because it's exactly 12 atomic mass units. Now, an atomic mass unit is extremely small, and I also have given you the mass of that in grams. So when you look on the periodic table, however, you're going to look and you're going to see that carbon has a mass of 12.011 atomic mass units. So it is not exactly 12, and the reason for that is that we have an average. Carbon samples contain all three of them. So whereas carbon-12 is exactly 12, the mass of carbon-13 is going to be higher, carbon-14 is going to be even higher because it has more neutrons. So how do we calculate this average mass? Well, to find the atomic mass, the average mass of an atom, what we are going to do is we are going to get the mass of a particular isotope. So let's say isotope A, and we're going to multiply it by the percentage of isotope A in that sample. To that, we add the mass of isotope B times the percentage of B in the sample. And we continue. So if we have a third isotope, we will go ahead and take its mass times its percentage. If we have a fourth one, we take its mass times its percentage, and we add them all up. And that answer that we get is the average atomic mass. I mentioned that carbon-14 was radioactive. It is an unstable form of carbon. Now, the reason for this instability has to do with the ratio of protons and neutrons in the nucleus. Protons and neutrons are held together in the nucleus by something called the strong nuclear force. And if you do not have the correct ratios, or if your ratios of protons to neutrons are unfavorable, then we have a nucleus that is likely going to break up into something more stable. And in that process, it also releases energy, which is the basis behind nuclear energy. So what I want to do right now is I want to show you a table that gives you an idea of what I'm talking about in terms of stability and ratios of protons to neutrons. So in this particular table, taken from a book called An Introduction to Chemistry by Mark Bishop, this is actually an online textbook, and you could check it out. In chapter 16, where he talks about radioactivity, talks about nuclear chemistry, he has this table where he shows the if you were to have a certain number of neutrons, a certain number of protons, this red line shows a 1-to-1 ratio. So if you have 20 protons and 20 neutrons, you're falling right on this line. Now for your very, very small atoms, such as carbon and nitrogen, the most stable form of that atom is when you have a 1-to-1 ratio. You'll see that this band of stability is pretty close to 1-to-1. So for carbon-12, where you have 6 protons and 6 neutrons, you're within this band of stability and you have a stable form of carbon. But if you have carbon-14, you have more neutrons and protons, you're falling outside or above this band of stability, and you have a radioactive form of carbon. The higher up you go in terms of number of protons, however, we find out that you have to have a greater than a 1-to-1 ratio. So if you had 60 protons and 60 neutrons, you would be outside of this band of stability. It would not be a stable form of that element. But if you have 60 protons, you want to have approximately 80 neutrons to fall within this band of stability. Again, if you're outside of it, then you have a radioactive form of that element. Whenever we have an unstable nucleus, and that nucleus is going to undergo a process by which it breaks up into something more stable. We're only going to look at 3 processes by which it breaks up into something more stable. There are other methods, but we're only going to look at alpha decay, beta emission, and gamma emission. So what is going on here? Well, alpha particles are actually a group of protons and neutrons that have a mass number of 4, in other words a total of 4 protons and neutrons, and an atomic number of 2, so there's 2 protons. So this grouping that would break off in an alpha decay would be a group of 2 protons and 2 neutrons. So 2 protons and 2 neutrons is actually the nucleus of a helium atom. So an alpha particle is, while it's referred to as an alpha particle, could also be referred to as a helium nucleus. So if you have something that is undergoing alpha decay, you are going to have this grouping of 4 particles breaking off from the central nucleus. So 2 protons and 2 neutrons being lost. And so here's an example of uranium-238, an unstable form of uranium. The 2 protons and 2 neutrons leave, and that process also gives off energy. Now in the process of leaving, they're going to change the identity of the element. So this is a process, or this is a representation of the loss of those protons and neutrons. This representation shows this radioactive decay. The thing about these is that you'll notice that the mass number, 238, can also be found on the other side. You have to conserve that. So 234 plus 4 is 238. Your total number of particles in the nucleus has to be maintained. Your atomic number, 92, if you go to the other side, you will also see that these 2 things added together give you 92. So since 2 protons are leaving, the remaining piece must have 90 protons left over. And instead of it being uranium, because 92 protons means uranium, 90 protons means thorium. You have a brand new element. So in alpha decay, we have our uranium-238. We're losing an alpha particle. So you see a mass number of 4 here, so 234 gives you the remaining particles needed to give you 238 for the mass number. And then for your atomic number, you have 2 here, so that means you have to have 90. If you look on the periodic table, that's thorium. Beta emission is the ejection of a particle from the nucleus, just like in alpha decay. However, this time it is going to be the emission of what's called a beta particle, which is also an electron. So an electron that did not exist in the nucleus before is being given off by the nucleus. The mass number of an electron is 0. The charge, well, it's not really the charge, but the number of protons, since it's the charge is opposite of a proton, we give it an atomic number of -1. The reason why we do this is because if an electron is given off, it's going to actually change the number of protons in the nucleus, and we'll see that in a second. So the way in which that happens is that if we were looking at an example of iodine 131, what happens is a single neutron becomes a proton. So it is changing its identity. In order for it to become a proton, it has to give off an electron. So an electron, which was not there before, is given off by the nucleus. And again, that also gives off energy. So it might make a little more sense if we look at the formula. If we go from 53 to 54, so we've increased the number of protons, but we had to give off an electron. And 54 plus -1, maintains that 53 that we had before, so the atomic number is conserved. Likewise, since we're giving off an electron which has no mass number, you'll notice that the mass number of both of these stays the same at 131. And so again, we have our iodine, and if we are conserving our mass number, we have 131 on both sides. If we're conserving our atomic number, this has to be 54 in order to maintain that. And an atomic number of 54 tells us that we have xenon. Now gamma emission, the last one we're going to look at, gamma radiation is just energy, it's light energy. There is no atomic number or mass number associated with it. It's just a process by which the nucleus is giving off energy. And so if we were to have an example of a atom that had a very, very high energy, so let's say that we have cerium 140 with an atomic number of 58. If we were giving off gamma radiation, if we're giving off high energy from this process, because there is no change, then all we're doing is ending up with the same atom, but this time without the same high energy. A lot of time what you'll do is you'll see a little asterisk beside the 1 signifying that this has high energy.